in a previous video, I did this. I found the electric field on the z-axis due to this line of charge with a charge density lambda. And it was fine. Everything's great. And I do have the electric field in the z direction is that. We found the electric field in the x and y direction. Well, we didn't do y. And the x direction was 0. We did that. Yeah, I didn't do y. Okay, so now I'm going to do it numerically. So let's erase. I want to keep that value up there because we're going to use that again to check our answer. So how do we do this numerically? What we want to do is, instead of breaking this into a infinite number of infinitely small pieces, we're going to break this into a finite number of just small pieces. Okay. So again, we're going to do the same idea. I'm going to say, here's my length of charge. I'm going to break this into finite charges. I'm drawing them right there. And then each one of those is going to have a vector position. We'll call that RQ. I'll have my observation location over here. I'll call that RO. And then we'll find the vector R right there. And then I'll say dE, due to that one liberty charge, technically it'd be delta E, is 1 over 4 pi epsilon naught dQ over the magnitude of R squared times R hat. And then the electric field is just going to be the sum over, I'll call it delta E. I'm going to add them all up. So there's a couple things. One, how do we find R? R is going to be RO minus RQ. How do we find dQ? Remember, before we used lambda. Well, we can still use lambda, right? I'm going to pick the step size here. Let's call it dx. So let's say dx is 0.01. We do, no, let's say 0.001. We do need to use numerical values here. So I'm going to pick values for everything. We can't do this with just variables. They have to have numerical values. If I have that, dx dq is just going to be lambda times dx. So here's what we're going to do. I'm going to put a charge right here. I'm going to calculate the electric field based on RQ and RO and everything I know. And then I'm going to move up to the next charge and calculate the electric field. And then I'm going to move to the next charge and calculate the electric field. And we're going to do that. And it'll be great. And we're going to do it in Python. I will make a visual at the end, but we're not going to make this a big visual thing, although that we could. Okay. I think we need to get started. So I'm going to jump over here to Python. I'm using WebVPython. Now I do need some values. So I need values for L. I'm going to pick a value for L. Let's say L is 0.1, 10 centimeter long rod. I don't know why. I need to pick a value for Z. Let's say 0.05. And these are in meters. I need the 1 over 4 pi epsilon naught. That's K. K is 9 times 10 to the 9th. And I need the charge density, lambda. I'm going to call this lam because lambda is a reserved word. And let's say 9 times 10 to, let's say 5 times 10 to the negative 9th. I'm just making up stuff here. I don't know anything, people. Okay, now there's one more thing I need to know, and that's dx. What's my step size? I said was 0.01. Okay, now we're all set. The first thing I'm going to do is just pick my own, I need dq. dq is going to be dx times lam. I need that. Let's go ahead and just move my q's and print the values of all the q's and just see if it's kind of working. So what I'm going to do is say rq is equal to the vector, not that, vector, negative L, 0, 0. So I'm going to start at the negative x direction, and then I'm going to move along. And then I do want to say something called dr, the step size. I need to move it as a vector, and that's dx 0, 0. I'm moving in the x direction. Oh, wait. I need my observation location. RO is vector 0, 0, z. Right? I know what z is. So what I'm going to do is say while rq dot x is less than L. So I'm going to keep on moving my rq until I get to L. And so all I'm going to do is print rq, which is the position of that charge, and then I'm going to move rq. So rq equals rq plus dr. And that's it. Now, you always have to be careful doing these kind of loops. It's possible that you could end up in an infinite loop. by never getting to that final thing. I'm pretty confident here though, because look, I'm moving in the x direction and I'm starting in the negative direction. So I will get there. I should. And there you go. There's all my positions. So they start at negative L and they go all the way. So that's good. It looks like it's working. Now I can calculate, use all that stuff to calculate the electric field. So down here I'm going to put, I'll make this a little bit bigger. I like it like that. Okay, let's just say I need to calculate R. R is going to be RO minus RQ. That's what we said before. I don't even need to calculate it. I'm just going to put it in there, make Python do it, and that's good enough for me. With that, I can calculate the electric field due to that. dE is going to be K times dQ, which I already have, times norm R. Remember, norm R returns the unit vector in the direction of R. So that is R hat. I don't have to do all that stuff. And then I can divide by the magnitude of R, again, the built-in function in Python. You give it a vector, it returns a scalar, and that's squared. That's the electric field due to that one charge. Now, how do I add that up, right? What do I do? What do I add it to? Well, I don't have anything to add it to. So I need to make an electric field vector 0, 0, 0. I need a starting electric field. Now, once I calculate dE, I can add it to E, and after I'm done, I'll have my total electric field. So over here, I'm going to say E equals E plus dE. So I'm going to add that to the total. Every time I go through there, I'm going to add to the total. Guess what? We're done. All I need to do, once I'm done with the loop, is print it. So print E equals E newtons per coulomb. Let's run this thing and see if it works. Okay, so there I get. Now, a couple things to point out. Remember, we said that the x component was 0, and here it's not 0. Okay, that's okay. It's close to 0. Look, this is 1,609, and that's 3, so it's really small. Okay, but the thing is, it's not going to be exactly 0 if I have depending on how many steps I have. Okay, so if I make my step size smaller, I'll get a better answer, but I'm going to leave it as this for now. What I want to do is to compare the z value with the theoretical value. So let's calculate ETZ, the theoretical z component. So I'm looking at the board right here. I have K times lambda times 2L divided by z times the square root of L squared plus Z squared. That's what we got before. I'm going to print that. Print ETZ, T for theoretical, Z for the Z component. Okay, and let's run it, see what happens. And then I'm going to do one more thing. So you'll notice the Z component of this, 1609.97, 1609.96. I mean, that's pretty good, right? That's pretty good. Okay, so impressive. Now, let's just go ahead and visualize this whole thing, because I think that shows the power of this whole thing. What I'm going to do is to put spheres every time I put a Q, and I'm going to put a sphere where the observation location is. After that, I'll come back and add an arrow for the electric field. And we can make this way better, and if you want, I will, but let's just go ahead and do this. I'm going to say OBS is a sphere. Its position is equal to RO. Its radius, let's make it small, L over 80. I don't really know. Now down here, every time I make I have an RQ, I need to put a sphere there. I'm not going to give it a name. I'm just going to put sphere, position equals RQ, radius, make this even smaller, is L over 100. And then color is color.yellow. So that, I have a name for that location right there. This other one, it's just going to draw a sphere. So every time I'll put a sphere there. And now there's my line of charge, there's my observation location. Remember, it's in the z direction. So x is this way, y is that way, and z is out of the board towards you right there. Okay, so if I can rotate this around, you can see there's my point. Now I'm going to put an electric field vector there. The arrow has a length, but the electric field is in newtons per coulomb. So I need a conversion factor from electric field to distance, and we're going to call that E scale. Now notice down here, I'm in the range of 1,000 newtons per coulomb. So if I just plotted this electric field, it would be a kilometer long, and that's 10 centimeters long. So I want it even smaller than that. Let's just try, we can change it. Let's just try a value. I'm going to make a value called E scale, and it's going to be 1 times 10 to the negative fifth. And if it's too small or too big, we can change that. Now down here, after I calculate E, I'm going to draw an arrow. I'm not even going to give it a name. I'm just going to draw it. Arrow is an object. It needs a position, and I'm going to put it at the observation location, which is RO. It needs an axis, which is the vector from the start to the end. And so in this case, it's going to be E scale times E. E is a vector. I've already calculated that. And then, of course, I need a color. Color is color.cyan. You can pick whatever you want. Okay, let's run that and see what it looks like. So there's my arrow right there. You can't really see it, but if I rotate around, zoom out a little bit, see there's my electric field arrow. That's kind of cool, right? Okay, but here's the real power of the numerical calculation. You can even see the little individual points there. What if I want to move the observation location over here to the end? Well, that's pretty easy to do. Over here, the observation location of 0, 0, Z, I could change that to L, 0, Z. I can, and I'm going to run it. And where is my thing? There it is. There it is. Right there. Let's change that. I can change it again. I don't need, let's put this at L, Z, 0. Let's do it in the Y direction. It'll look a little bit better. There we go. And so you'll see that the electric field here has a Z component, in this case Y, and an X component because we don't have that even integral, that odd function integral over an even limit, and that would cancel and get 0. It's non-zero here because we don't integrate over a symmetrical unit. Okay, if you wanted to, and we could do this, we could put a whole bunch of electric fields all around this thing and see what it looks like. But I really just want to introduce you to numerical calculations first, and that's that. So the link to this code is down below if you want it, and that is that. I will talk to you later.